In this lesson, I'm going to be talking about length contraction. This is the second consequence of Einstein's theory of special relativity. In the previous lesson, we explored the idea of how time becomes warped as you approach the speed of light, and that different observers experience different times. That's known as time dilation. In other words, moving clocks run slow. The formula is quite simple. T is equal to T sub naught over the square root of 1 minus V squared over C squared, where T sub naught is the time measured for the moving, according to the moving observer, and T is time as measured according to the stationary observer. Okay, suppose you have an observer looking on and seeing someone else moving. This is the time given as measured by the stationary observer. Let's get into length contraction. So there's an idea that as you move close to the speed of light, according to Einstein, space contracts. Okay, that's called length contraction. Okay, moving close to C, space contracts. In other words, moving objects are shortened along their direction of motion, as we'll see. Let's look at a simple example. Suppose you have a spaceship, okay, moving at some velocity v to the right, and it's moving towards the star. Okay, so the spaceship is taken off from Earth, it's moving towards the star, and the distance between the spaceship and the star is L sub naught. Let's call it L sub naught. So we can write an expression for L sub naught in terms of the velocity and time it takes for the spaceship to reach the star. L sub naught is equal to Vt. In other words, V is equal to L sub naught over T. Okay, for an observer on Earth. So the observer on Earth, let's see the velocity of the, would measure the velocity of the spaceship as being its length. Apologies, it's a length like this, divided by the time it takes to reach the star, time t. Now the distance traveled by the spaceship to the star, let's call that L, it's equal to V T sub naught. Okay, because T sub naught in this case, because the it's in the observer's frame of reference of the moving spaceship. Okay, and the times are different, T sub naught T, because of time dilation. But since V is equal to L sub naught over T from above, we can rewrite L here as L sub naught T sub naught over T. And since T sub naught T is equal to this, square root of 1 minus V squared over C squared, by rearranging the time dilation formula, we find that L is equal to L sub naught the square root of 1 minus V squared over C squared. And this is the length contraction formula. Okay, where L is the contracted length of the moving observer, and L sub naught is the length for the observer at rest on Earth. So the moving observer would have their length contracted according to someone on Earth watching by. Okay, so suppose the spaceship looks like this in its rest frame when it's not moving. As it approaches the speed of light, suppose it can move at 99% the speed of light, it'll look something like this. It'll get flattened. Okay, but for the person in the spaceship, they wouldn't notice any difference because they're moving with the spaceship. And according to them, they're stationary. Everything else, including the Earth, is moving. Okay, which is from Einstein's law of relativity, the case of symmetry. So the spaceship gets shortened, contracted along its direction of motion. Okay, not perpendicular to its motion, but along its direction of motion. So V equals 0, you'd see this for the spaceship on Earth at about, let's say, 99% speed of light. You would see it like that, flattened, contracted. Let's do an example to see how this works. Let's suppose the spacecraft has a length equal to 20 meters, I should say 50 meters, okay, on Earth. And it travels at 99% the speed of light, 99c, 0.99c, okay, to a star, which is 5 light years from Earth. Let's find the length of spacecraft when it's traveling at 99% speed of light, as measured by 1, the astronaut in the ship, in the craft, and 2, the observer on Earth. Okay, part 1. So the astronaut on the ship, as I mentioned before, won't notice any difference in the length of the spacecraft. So they'll just see 50 meters. Okay, the length is 50 meters, quite simply. Okay, because they're at rest relative to the spacecraft. Part 2, the observer on the Earth, they will notice a contraction, as I mentioned before, in the direction of motion. So using the time dilation formula, the length contraction formula, L is equal to L sub naught square root of 1 minus v squared of c squared. So L sub naught is the length of the spacecraft as measured by the observer in the spacecraft, which is 50. Okay, the square root of 1 minus 0.99 c squared over c squared. That'll be 7.05 meters, which is significantly less than 50 meters. So that's what the person on Earth would see the spacecraft's length, okay, significantly shortened. And that's how length contraction works. So moving objects experience a contraction along their direction of motion.